Hello, my name is Anton Kolonin, and today we are going to talk how OpenCog and SingularityNET Unsupervised Language Learning project is using graphs supported by Aigents Graph subsystem. To start with this, let's go to Graphs demo, and for starters, let's explore capabilities of Aigents graphics framework. And for example, let's consider OpenCog atom type hierarchy, which is present in GitHub, and it renders different sorts of atoms and nodes and links, entire hierarchy of objects used in OpenCog, and this file can be loaded and rendered as a graph. So let's see what can we do with this graph. First of all, we can play with slicing. Slicing can be vertical, horizontal, and slicing can be applied for the situation when different types of nodes are present on the graph. On the OpenCog atom type hierarchy, there is no different node types, so every node is just a type. So we are not interested about this. We'll see how slicing is working with other graphs later. Further, we can change node radius, so we can nodes larger, or we can make them smaller. Let's keep them this way. And also we can select the layout. So if we specify a threshold for layout, then layout is created using the forces. And the now amount of threshold drives when we stop iterations. So if threshold is high, then iterative layout using forces pulling and pushing nodes apart and together, so that links are pulling nodes together, and each node pushes another node apart. So, and in iterative process, nodes are trying to rearrange themselves on screen, and they continue until they reach threshold on changes of the positions of the nodes on the next iteration. So if we decrease threshold, then nodes become more and more sparsely distributed across the screen. And also we have balance. So balance means that if the balance is low, then nodes are being pulled by links stronger, and they are pushed apart less. So if we increase threshold, pushing apart becomes more important than pulling together. So nodes are becoming spread more evenly. So we can play with this as well. Also, we can turn the layout off, and if the threshold is turned off, the nodes are arranged accordingly to some kind of natural order. Natural order means that horizontally nodes are sorted alphabetically, so we see atom, arithmetic, boolean at the beginning, alphabetical sorting, and we have unordered and value and variable at the end. So horizontal direction implies alphabet, and vertical direction implies rank or reputation or importance of the node in respect to other nodes. Like the more linkages node receives from the other nodes, the greater its importance. Like we see that there is a link node which has a lot of connections from the other nodes, and it's at the very top. And because it itself links atom, so the atom gets all importance that is received by link. So reputation is flowing through the link to atom, so link and atom are residing at the same level. But if we select something below, we'll see that this particular node has no any incoming links, so its rank or reputation is low, and it stays at the very bottom. So if we don't have threshold set for force-directed layout, then nodes are spreaded using this natural sorting. Further, if we still want to apply force layout, we can do it in different ways. We can say that the force layout is applied only horizontally. So in this case, vertical sorting, given the rank, stays. So we still have atom link and value at the top and a bunch of non-linked nodes at the bottom. If we change power directions to vertical, then we have quite different picture. So the nodes are keeping alphabetic sorting. So we see nodes starting with A at the on the left, and everything starting with V on the right. And if we select both directions of force layout, of force direction, then we see nodes are spread evenly across the string. And finally, we have node filter here. So here we can do the search. For example, if I'm interested about inheritance, I am type it in, press enter, and here I see inheritance link and all its connections. And also I can use this filter implicitly by clicking on nodes. So if I click on ordered link, it is automatically substituted into the filter, and now I see ordered link and unordered link because it's matching the text filter. So all nodes matching the filter, and all neighbors of these nodes are appearing on screen. So that was just discussion on how we can play with different properties of graphs, given OpenCog atom type hierarchy as example. Now let's move to SingularityNET and OpenCog Unsupervised Language Learning Project graphs. There are few sorts of graphs: mutual information, word census, link grammar, categories, and parses. So let's view them in some order. But first of all, let's consider the source file used to produce these graphs. So that's what we call proof of concept English corpus. So it has some bunch of simple sentences with some words in these sentences, and what we are trying to do with these graphs, we are trying to render different linguistic structures and linguistic data extracted from this text programmatically. So the first thing that we can extract from this text is what we call mutual information. So what mutual information does, it takes the text and it takes all sentences of the text and it breaks the sentences into words, and it computes mutual information between the words. Like if the words are occurring together in the sentence, they are given some bump of mutual information. So the words that are staying in the sentences close one to another more often than other words, then these two words are getting more mutual information. So in this graph, we can check the neighbors of the words. Like, for example, if we take word off, then we can see that it has highly linked neighbors, board, and directors. Like, I think that's because of sentence like board of directors is used more than once. And other words are getting more thin connections, so they are repeating together less often. Okay, let's try something else. Let's take once. Okay, once is linked to, I believe, his. To make it more clearer, let's turn force directed layout. Let's turn it both directions, so the words of interest are staying in the middle. So we see word once, and it has a significant amount of mutual information in respect to word her, and the word and so the her is more and daughter. So something was repeating often with daughter and her, with word once was repeating often enough with words daughter and her by some reason. We can explore this text. So that's and we can remove the filter and see it all again, and we can improve the force directed layout. So that's mutual information. Based on that mutual information, we do the parses. So what we do in these parses, we take a sentence like a mom is a human, and we create links. So let's say in the sentence a mom is a human, every word is enumerated like left wall or left boundary of the sentence given number 0, a is 1, mom is 2, is 3, a is 4, and so forth. So here we are given sentence like a mom is human, a human, and further we can have more parses. That's not parse of the entire text. Here we have just a few sentences, but we can substitute the whole text here. And by the way, we can see how the full parses are looking like. Let me put it here. So here is the whole bunch of parses. We can read these parses and render these parses in the graph. Okay. And the parses can be rendered in a few different ways. Here we just take the links across the parses and we see which words are linked more often. So it's most like mutual information that we have seen before, but it's more, but it's not about co-occurrence in the sentence. It's about linkage in the sentence. So we see that the left wall is linked with is often enough. We can select the node and we can see relative strengths of linkages of a given word compared to other words. Here we see that most of verbs, for example, are linked with left wall, and left wall is often strongly linked to the period in the end, for example. Another kind of looking at the parses is looking words with sentences, so phrases with words. So here we see different phrases like mom like cakes and all words that are occurring together with mom likes cakes. We can take word cake and see all the sentences that are contained in the word cake, and we can play with different layouts. So we can have all words at the top and sentences at the bottom. We can play with layouts, so have more smooth distribution of nodes across the string. And we also can view the parses, so we see both phrases with linked words, everything. So the picture is more complex, but again we can use filter to select some sentences, and we can also play with turning different nodes and links, by the way. So we can turn off the phrases, so now no phrases rendered, and we can turn off the words, so only the selected word is used. So if we remove selection of this word, we see only the phrases. Now we get words again. And also we can remove particular sorts of links, like we can remove words links between phrases and words. So we see only links between the words, and we can remove links between the words and see only the links between sentences and the words. Well, so that was about viewing the parses on the graphical representation. Another kind of information that we can render with this graphics framework is word sense disambiguation data. Word sense disambiguation process is intended to split different meanings of the same word in different contexts. Like, let's say we have word board, which can be either board of directors, board of sheep, or whiteboard in school. And these words are appearing in context of different words. Like sense board of directors is appearing with words company, directors, enterprise. The word board as board of a sheep appears together with sail and sheep. Whiteboard as a board appears with chalk, school, white, and right. Similarly, and that's by the way called semantic disambiguation, because all meanings of board are still under category of nouns, so that's just a noun board with different meanings. We still have another kind of ambiguity. It's about grammatical ambiguity, where we have word saw, which can be either noun and indicate some tool which can be used to cut the wood, or it can be a verb, past tense of the verb see. And different kinds of saw appears in different contexts. Like saw like a wood appears together with wood, and saw like him or her appears with words clearly, her, yesterday, him, etc. Again, we can play here with nodes, like we can remove visibility of nodes that are not interested to us, like we remove sentence and we see only the words, and we can remove words, so we see only the sentence, and we can play with different links, like we remove links between words and sentences and see only the links between different senses of the same word, or we can do it the other way around. We can just see only the links that are indicating particular sense. And also we can play with different layouts, like we can remove force directed layout and have the hierarchical arrangement of the nodes, or we can turn the force directed layout and have the arrangement only horizontal. So we see some natural hierarchy of the word and sense usage in our graph. So that was about disambiguation graphs. Now let's move to what we have, what we can do with these parses that we were seeing right now. Once we have parses, we use a grammar learner component to infer categories of words based on the parses and different contexts of the words. And in particular, in our project, when we do the categorization and classification of the words and further grammar induction, which we'll see later, we use not a word embeddings, we use not a word context, but we use what we call disjuncts. So disjunct is something like if there is a, let me give you example. So if there is a word liked in the sentence, then the word liked has three different connections. We have word liked to mom, we have liked to cake, and liked to before. So the combination of mom on the left, cake on the right, and before on the right, three words with different positions relative to the word of interest, the word liked. So the whole context of the word liked called disjunct. And in fact, this kind of disjunct could suit different words like mom loved cake, or mom love cake, or mom like cake, or mom eats cake. So different words can suit the same disjunct, and in this case it's suitable to talk about lexical entry. So there is a unit of the words on the left and on the right that describe particular context which can be filled particular part of speech, like a verb in given sense, or a noun of different category. So we consider every word in the parse, we identify disjuncts of this word, and then we try to classify these words and to build category tree like this one. And we can clearly see that given the same corpus, where is it? Let me go back to the corpus. Here is the corpus that we actually parsed and that we actually use it to build this categorical tree. We can see some interesting branches. So some branches are not good because our technology is not perfect, but some branches are quite reasonable. For example, we can see the categorical branch daughter, which has child nodes daughter and son, and then node accumulating daughter and son is child node in respect to node accumulating dad, daughter, mom, and son. So dad and mom are being added to the hierarchy, to the tree. Also we see hammer, saw, and telescope, and I guess the saw is implied as a noun here, not a verb. And we see that actually hammer and telescope are more specific category, unifying hammer and telescope together. So both hammer and telescope are kind of tools. And again, as in all previous graphs, we can do some funny things about the properties of the graph. We can change we can make it looking that way or that way, and play with different layouts that we discussed before. And also we can explore particular branches of hierarchy and see the nodes of our interest more closely. And by the way, if we don't need our categorical tree to be rooted, we can remove a rooted flag and just see different subgraphs placed separately. And we can add force layout to this, so the nodes are pushed apart to greater extent, something like this. Okay, so that was about categorical tree. Now the most interesting part of the story in the end of our language learning process is grammar. So when we have the parses like that, and when we have categories learned from these parses like that, we can infer the grammar. And the grammar is actually the standard link grammar dictionary exported so it can be loaded into link parser of link grammar project, and then this dictionary enables to do actual parse of the text in given language. Of course, if we have trained data to infer the grammar substantially rich to cover all possible combinations of words in the test corpus. So this kind of graph is more complex and it has layers. It has 4 layers actually. At the layer number 1 we see words. So we see word wood, and by the way, let's use our tools like let's see here. So we have categories. So let's say we remove everything except words. So here we have words only. Now, besides words, we have categories of words. So here are categories. So we have identified in this simple corpus 1, 2, 3, 4, 5 categories of words. Then after categories we have something that we call disjuncts. So disjuncts are combinations of different contexts that are describing each category. So like it can be thought that if we have let's say, let me consider something simple. Okay, let's do this. So if we have category C01, then this category C01 is used in 1, 2, 3, 4, 5, 6, 7, in 7 grammatical contexts. And each grammatical context is a disjunct, and this disjunct in turn has some connectors. For example, this particular disjunct has only one connector, and connector is something that points to some neighbor cluster. For example, if we have cluster C01 and it has disjunct consisting of C02, C01 connector, so it points to C02, C01 connector. So the layer number, let's remove something, the rest. So the layer number 3 is layer of connectors. Connectors are grouped by disjuncts, and disjuncts are used by categories, and categories are representing words. Also, we can play with different links. So let's say we want to remove all links between connectors to disjuncts. We can remove links between words and categories. That's was all about the graphs, how they look. And now let's move to the code, how it's actually working. So here we see the source code of the page that we've been looking at. It uses jQuery. So jQuery is used just for general purpose HTML rendering. We also use Aigents AL JavaScript, which has some basic functions used by Aigents Graph subsystem. So the Aigents Graph subsystem is the one that is used by OpenCog and SingularityNET and Supervised Language Learning project. Let's consider how we render, for example, the parses. So that let's better take grammar. Grammar is more complex and it will be more interesting. Okay, so here is the grammar, and let's search for grammar. Grammar. Okay, so we have function do grammar graph. So that's bound to button do grammar graph, view link grammar. So then if we click on the link view link grammar, we have the link grammar graph. Fair enough. So let's see how this function works. So this function calls Aigents Graph request graph popup, which actually renders this popup. So this popup is rendered by the request graph popup. It has the title. It has ID of the placeholder HTML control. Let's look at this. Where is it? It should be somewhere in the HTML file. Well, it seems like it's created behind the scene. So we can actually use different HTML IDs Now it has reference to the control, HTML control that is used to load the file name of the link grammar dictionary file, and then it has function builder. So what happens by request graph pop-up, at some point it tries to get this path, it tries to load the file, and the file is loaded, it passes the text of the file into the builder function, and the builder function continuous initialization of the Aigents Graph framework. We can specify configuration, and in this configuration we can identify multiple things. First of all, we identify colors. So remember, here we have different colors of the nodes, like words are white, categories are yellow, disjuncts are green, and connectors are violet. So here, oops, wrong tab, let's close this, close. So here, so we have these different colors, and the different colors are set for links, like plus, minus, VC, CD, as well as for nodes, like connector, word, disjunct. Then also we have slide, and by the way, if we don't specify colors for links and nodes, they are rendered with default color, like yellow color is default for nodes and blue color is default for links. Further, we can specify the order of slicing. Remember that we have connectors, then disjuncts, then categories, then words. So here we have this connector, disjunct, category, word. Further, we can have option to have links labeled. So you see, so we have labels of links, like WC is word category and CD is category to disjunct. So the links are labeled, we have the background set. Let's check. Yeah, we have some gray background, nice. And then we have an important function, build links. So build links does something to take the text and build the links. And links is the most important thing to do. So the links are just typically triplets, like source, origin, and link type. And optionally there could be a link weight, fourth field, and the link weight is default is 1, but if you specify it, it can be any number. So if there is a number specified for the link, then the link is rendered with particular thickness of the connection between the nodes. And that grammar build links is very specific code. It's specific to particular file format. So here we just parse grammar in link grammar dictionary format that we use in Supervised Language Learning project. Let's go further and see how we can call graphs. So then, after we have built the links, we may need to specify orders of the nodes. So it takes to compute the order or rank of the node on graph, which can be used for vertical sorting. And by the way, besides vertical sorting, the rank of the node identifies color saturation, like the nodes that are having higher rank or higher connectivity with child nodes, they are rendered in more saturated color and they are placed high. Like we have category CO3 more saturated and higher than other categories. Similarly, we have connector CO3, CO5 more often used than others, and it's more saturated and placed higher than the others. And the same we see with disjuncts. For the words, there is no difference between, because all words are having no incoming links, so they there is just hang below the categories. So we have built the orders, and graph order class or graph order object computes orders of links in few different ways. Like we can compute order based on the directed links using liquid reputation or liquid rank algorithm. Also, we can provide some extra options for nodes. So the nodes is not necessary to get filled, but we can add more flavor to our graph if we add properties to node. Like we can add type. So we can the type is identified by is property, and also there is a key which can be used for sorting. So we can adjust key and is for some particular nodes that can be used for graph rendering. And once we are done with links, orders, and nodes and have config ready, we let the builder function to return all these guys, nodes, links, orders, and config. Config may be omitted, orders may be omitted, nodes may be omitted, so the links must be provided. And finally, we can specify what kind of slicing we want. Either we want vertical slicing or horizontal slicing. By the way, I forgot to mention that slicing can be horizontal. So that's not very useful in this given case. We have connectors on the left, this jumps closer to the middle. Then we have categories. Further on the right, and we have words on the very right. But I'm not sure if this kind of arrangement is practical here. So I would better stick to vertical slicing. And also we provide default layout threshold. So these parameters are used as default, and if we call once we call link grammar, these default parameters are used to create default graph. That's one example. Let's consider for another example how that's the simpler one. Census graph. Remember, we use it word census, and we have and let's actually see the source file. So the source file is let's go there. Okay, so this is the census demo file. It's pretty simple. We have just different words, and we have their meanings, and we have properties of these words specific to these meanings. So let's go to the code. So we have do census graph function, which is called when we click on view word census, and here we also provide the HTML ID to get the value and pass at path, and then we provide the builder function, which creates the config, which uses text to build links, and while building links, also the nodes can be filled by the build links algorithm. And then we just create the orders additionally based on the links that we have. And then we return the nodes with their properties, the links, the orders, and again config. And we specify some different properties for the graph, like there is no slicing, there is different layout threshold, there is different layout balance, and there is different combination of the forces used for force directed layout. And if you are interested, you can get this source code and explore it and try to use it in your applications. So that's all what I wanted to cover on SingularityNET and OpenCog Unsupervised Language Learning Graphs demo. If you are interested, then go to SingularityNET.io site and check LangLearn section of the site, and stay in touch and keep tracking our updates. Cheers, goodbye.